Hello and welcome back. In this presentation, we're going to look at the rate determining step and how we can use rate data to make predictions about the reaction mechanisms. In the previous presentation, we looked at the iodine clock. Basically, it was a pair of reactions occurring at the same time. One of them was producing iodine and one of them was destroying it. The reaction came to an end when the second part of that reaction, the destroying iodine, stopped and iodine was left over, and that would change the colour of the starch that was added to it. Now, there are different ways of doing this experiment, and one of the ways to produce the iodine in the first place is to use this, which is hydrogen peroxide. Now, if we get hydrogen peroxide and we add it to some iodide ions and some hydrogen ions, then what we get is iodine and water being produced. Now, if we look at this reaction here, you can see just how many particles have all got to get together to be involved in this reaction. There's the hydrogen peroxide, there's a pair of iodide ions and a pair of hydrogen ions. Now, of course, there's not going to be a simultaneous collision of 5 particles. It's going to happen in a sequence of steps. What we can do is we can look at the rates of reaction here to determine which of these processes are going to go first, which of these collisions need to happen in what sequence, and what the slowest part of that reaction chain is going to be. This is going to be called the rate determining step. Now, we could run some experiments here, and we could look at how the rate of reaction depended upon the concentration of the different elements of the reaction. So, first of all, what is the dependence on the concentration of the hydrogen peroxide? And we can see in this example, the dependence was to the order 1. And it was also to the order 1 of the iodide, but to the order 0 of the hydrogen ions. Now, first of all, if it's to the order 0, it means it's a 0 order reaction in relation to the concentration of the hydrogen ions. So that really doesn't affect the rate of reaction. So we don't have to include it in our rate equation. Our rate equation would simply be dependent upon the first order relationship towards the hydrogen peroxide and the iodide. It means that in this reaction, it has an overall order of 2, which is the same number as just the number of ingredients that are taking part in that rate determining step. A really good example of this is in this reaction, the hydrolysis of a haloalkane. So to understand this, let's go into all of the various parts. A hydrolysis is any reaction where the hydroxide, the OH- ion, basically attacks another molecule. In this case, it's going to undergo nucleophilic substitution. So the hydroxide being negative is going to go after the positive charge. That's why it's a nucleophile. It's going to substitute something that it is more reactive than. So it's going to kick out the bromine from this other molecule. Now, this other molecule is a haloalkane, which the halo comes from halogen, which is the bromine part of this, as using that as an example. And alkane, a long chain hydrocarbon, it could be of indeterminate length. It could be any length hydrocarbon really there. And because all of those reactions are the same, irrespective of how long it is, we could put a general formula where we've swapped out the alkane with the symbol R just to represent, yeah, this is an alkane of whatever length. And so RBr, so that's the haloalkane, it's going to be attacked by the OH-. And the OH is going to replace the bromide and kick the bromide ion out into solution again. And where do we get the OH- from? Sodium hydroxide would be a good one, because in solution, the sodium and the hydroxide ions separate, leaving the OH- to go seek down some positivity and become a nucleophile and displace something that it is more reactive than. So a real example of that could be this, bromoethane. And this comes under attack by the hydroxide ion. There's the swapping of the hydroxide ion with the bromide ion. The bromide gets kicked out into solution. Now, there are ways that we could detect the bromide being kicked out into solution. let's have a look at those. So the test for any of the halide ions is, of course, acidified silver nitrate solution. If you add silver nitrate, there will be a precipitate that forms in the presence of that ion. So when this reaction has concluded, what you will find is, well, for bromine, it's a cream precipitate. For the other halogens, it's a slightly different colour, but it's fundamentally the same. What you'd need to do is you'd start a stopwatch as soon as you have mixed the ingredients together, and then you would look through your conical flask at a cross painted on the desk underneath or on a piece of paper. And when that is obscured from your vision, you could stop it and use that as the total time for the reaction to take place. And of course, 1 over that total time would give you the rate of reaction. So here's an opportunity for you to work with some of the data. So first of all, the rate of reaction was measured against the concentration of the 2 main ingredients. First of all, the bromoethane, and then secondly, the sodium hydroxide. And what you can see is, yes, indeed, when you change the concentration of the bromoethane, the time it took for the precipitate to form was different. So there was obviously a dependence on the concentration of the bromoethane. When the same experiment was done against the concentration of the sodium hydroxide, it was found to be independent of the concentration of sodium hydroxide. So what you can now do is write the rate equation for this reaction. The best thing to do is, first of all, is to write a rate concentration graph for the data on the left-hand side there, and determine what order the reaction is with respect to the bromoethane. So I've done that, and you can see that this is what it looks like. It's kind of a straight line, though you could argue that there's a slight curve there, but imagine very simplistically that this is essentially a straight line. Then we would know that it was to the order 1, and so therefore the rate equation would look like this, that the rate was equal to the rate constant multiplied by the concentration to the power 1 of the bromoethane multiplied by the concentration of the hydroxide ion to the power 0, which is equal to 1, of course. Because it is not dependent upon the concentration of the hydroxide ion, it is to the power 0. It means we don't have to include it in the rate equation, because anything to the power 0 is just equal to 1. It means that the rate is equal to the rate constant multiplied just by the concentration of the bromoethane. Now this information, that the rate of the reaction is dependent upon the breakup of the bromoethane rather than the addition of the hydroxide ion, is something that we can use to make a prediction about the reaction mechanism. So here what we understand is that the part of this reaction that is concentrating the rate is the concentration of the bromoethane. It means that that must be the rate determining step of this reaction. It means that it can go no faster than this step. Like, this is the step that's limiting the rate of this reaction occurring. Now that means that there must be an intermediate step. It must mean in the process of that substitution, it doesn't just happen in one go. What first needs to happen is the bromide ion needs to separate before the hydroxide ion comes and joins along. Now, because we know that the rate of this reaction is not dependent on the concentration of the hydroxide ion, but it is dependent on the concentration of the bromoethane, it means that the slow part of this reaction, the rate determining step, is that first step, that intermediate step of the bromoethane breaking into 2 ions immediately before the hydroxide comes in, which you would call the fast step. So in summary, what we've been able to ascertain is by identifying which parts of this reaction are the parts of the reaction that's limiting the rate of reaction, we've been able to find which parts of this reaction limit the whole reaction taking place, and we therefore can assign that those parts of the reaction are as rate limiting step, and we can also infer the existence of intermediate steps occurring.